In this video, we are going to go over resonance structures. So let's start out by drawing a Lewis structure, and we'll see why Lewis structures do not always describe a molecule well. All right, so I'm going to draw a molecule down below. Okay, so we have a carbon that has 3 bonded atoms. 2 of them are oxygen, 1 is hydrogen. Carbon has a double bond with 1 oxygen and a single bond to another oxygen. So, are there any formal charges on this Lewis structure? Yes. Okay, so let's go through and figure out where that formal charge is. Is it on the hydrogen? Nope, hydrogen has 2 shared electrons, so it's happy and neutral there. It doesn't have a formal charge. What about the oxygen that is double bonded to carbon? So I'm going to label that oxygen 1. We'll label the other one oxygen 2. So looking at oxygen 1, does that have a formal charge? So let's go through the calculation for formal charge. So we have 6 valence electrons for oxygen, and oxygen 1 has 1, 2, 3, 4 lone pair electrons, so we'll subtract that. And we're going to subtract half of the shared electrons, which is also 4. Okay, so 6 minus 4 is 2. 2 minus half of 4 is 0. Okay, so oxygen 1 does not have a formal charge. What about oxygen 2? So again, we have 6 valence electrons for oxygen. Oxygen 2 has 1, 2, 3, 4, 5, 6 lone pair electrons. And then we'll subtract half of the shared electrons, which is 2. So 6 minus 6 is 0. Minus half of 2 is negative 1. Okay, so oxygen 2 does have a formal charge. So we're going to put a negative symbol in a circle next to that oxygen. Okay, so now let's talk a little bit more about this Lewis structure. Okay, so we have a single bond between carbon and oxygen 2, and then we have a double bond between carbon and oxygen 1. Which bond is longer in length? So is that the single bond or the double bond? The single bond. So remember from our review in chapter 1, we said that single bonds are longer than double bonds. However, if we run this molecule through some experiments to figure out the length of those bonds, we would actually find that those 2 bonds have the same length. So here I'm going to label these bonds with numbers. In actuality, 1 and 2 have the same length. So why is that? Why do those two bonds have the same length if they're different? Well, this has to do with resonance. So this is where Lewis structures fall short because they don't really show resonance in a structure. So in actuality, the first bond and the second bond that we labeled before, instead of being a full double or a full single bond, we actually have something that's kind of in between for both. So we show a dotted line to indicate that the electrons in the double bond are actually delocalized along both carbon-oxygen bonds. I'm going to add in the lone pairs here. So instead of one of the oxygens having a full negative charge, each oxygen has a partial negative charge. So one oxygen has a negative 1/2 charge, the other one also has a negative 1/2 charge. So the electrons that were contributing to the negative charge on oxygen in our first Lewis structure, those are actually shared between both oxygens. So the pi bond or double bond electrons are delocalized along both CO bonds. And again, this is verified through experiment. Okay, so let's look at some examples of resonance. We're going to start with something called an allele cation. So I'm just going to draw a molecule here. So the carbon on the right has a positive charge. All right, and let's go through and figure out the hybridization scheme for each carbon. So I'll label the carbons 1, 2, and 3. So what is the hybridization scheme for carbon 1? Is it sp, sp2, or sp3? So carbon 1 is bonded to 3 other atoms, and it doesn't have a lone pair. So it should be sp2. What about carbon 2? Is that sp, sp2, or sp3 hybridized? So carbon 2 is also bonded to 3 atoms, and it doesn't have any lone pairs, so it would be sp2 as well. And what about the third carbon? Is that sp, sp2, or sp3 hybridized? So this one's a little trickier because it has a positive charge, right? However, it is also bonded to 3 other atoms, and it doesn't have any lone pairs, so it is sp2. Easy peasy. Okay, so now, if you recall from our review of hybrid orbitals, whenever we have an atom that is sp2 hybridized, there is a leftover p orbital, at least for carbon, right? So remember our energy diagram, and we had 1s, 2s, and then our 2p orbitals. And for carbon, our unhybridized energy diagram looked like this. And for an sp2 hybridized carbon, we were combining the 2s orbital and then 2 of the 2p orbitals. So eventually, we ended up with three sp2 hybrid orbitals and one leftover 2p orbital. And then we had our 4 electrons distributed among those orbitals. So that means that each of these carbons has a p orbital hanging out. So let's draw that. Let's see what that looks like. So I'm going to redraw the carbons. Oops, accidentally changed slides. So I'm redrawing those 3 carbons, and then I'm going to draw a p orbital on each of those carbons. Because remember, they're all sp2 hybridized, so they each have their own p orbital. All right. Now, carbons 1 and 2 have a double bond between them. So that must mean that they have opposite spin electrons that are then pairing up to form a pi bond. And then the single bond is a sigma bond in the middle. Now, carbon 3 has a positive charge, which means it's missing an electron. So we'll just write a positive sign there, and we'll say that that is empty. And it is possible to have an empty p orbital. Okay, and then let's draw our hydrogens just to stay consistent here. Just kind of show them hanging out. All right. Now, what's really interesting with resonance structures is, again, electrons are delocalized. So the electrons that are forming the pi bond can actually move over or be shared between all 3 carbons. So it's just as likely that we could have a double bond between carbons 2 and 3, right? There's nothing saying that we can't. So maybe carbon 1 has the positive charge. Well, in actuality, the electrons in the pi bond, again, are shared equally between all 3 carbons. So I'm just going to redraw our picture from up above, but just show that carbon 1 can also have an empty p orbital, or a positive charge. All right, so on the left-hand side, and the right-hand side actually, we've shown resonance structures. And what we do with resonance structures is we put brackets around them. And then we also draw this double arrow here to show that that both structures are valid. Additionally, we show the brackets to indicate that this is not a reaction that's occurring. It's just showing that electrons are delocalized. And I sometimes will use the abbreviation RXN for reaction. Okay, so I'm just going to erase one of these structures, and I'm going to draw the hybrid structure. So this is going to show that delocalization of electrons. All right, so that double bond that was originally between carbons 1 and 2, or between carbons 2 and 3, is actually shared across all 3 carbons. So we almost have a 1.5 bond there. That also means that carbon 1 and carbon 3 are sharing that positive charge. So they each have a partial positive charge. And then sometimes what we'll do is just put 3 lines between the brackets showing the delocalization of electrons and the hybrid structure, just to indicate that the hybrid structure is a result of the movement of electrons. So resonance structures actually stabilize compounds because carbon doesn't really like to have a full positive charge if it can avoid it. So instead of having a full positive charge, it's going to share that charge with another carbon. And then that's going to lower the energy of this molecule and therefore stabilize it. So I'm actually, going to write up above, resonance structures stabilize the compound. All right. So let's look at one more example. We're going to look at a compound called an allele anion. So this is very similar to the allele cation. So again, we have 3 carbons, and we have a double bond between 2 of the carbons. We still have 5 hydrogens. Oops. I'm going to show approximate bond angles here. However, instead of a positive charge on one of the carbons, we have a lone pair of electrons, which makes it negatively charged. Okay, so let's do the same thing we did before. Let's figure out the hybridization for each carbon. So carbon 1, is that sp, sp2, or sp3 hybridized? It's exactly the same as our last example, so it is sp2 hybridized. What about carbon 2? Is that sp, sp2, or sp3 hybridized? sp2, again, it's the same as our previous example. But now here comes the tricky one, carbon 3. Is that sp2 or sp3 hybridized? So it has 3 bonds and a lone pair. So what is its steric number? So its steric number is 4. Okay, so we would assume it's sp3 hybridized, right? So let's just tentatively write sp3 for now with a question mark, because we're going to show that this has resonance, similar to our last example. So I'm going to show those p orbitals again for each carbon. Now, the carbon on the right, if it's sp3 hybridized, we technically wouldn't have a p orbital there, right? But bear with me for now. Okay, we've got our pi bond. And let's also show our hydrogens. So carbon would prefer to not have a full negative charge. It would prefer to share that with another carbon. And in fact, it can. So what can happen, is those electrons in the p orbital right here can move over or kind of move down to create a double bond. And then the pi bond on the left will break, and the electrons will move over to carbon 1. So I can also show this with some arrows on the left. So we're just showing the movement of electrons. I'm just going to erase these arrows here. All right, so let's show that movement of electrons. Okay, so if the electrons move over to the left, we're actually going to have a pi bond between carbon 2 and carbon 3. So these are our these are our resonance structures. And let's draw the hybrid structure. So the resonance structures show that those electrons can move around and delocalize so that they're actually shared among all 3 carbons. And this is going to stabilize our molecule. Okay, so this looks a lot like our hybrid structure from the previous slide, except instead of partial positive charges, we're going to have partial negative charges. So each carbon shares the negative charge, and therefore they're more stable. Okay, so looking at our hybrid structure, is the third carbon sp3 hybridized or sp2 hybridized? It's actually sp2 hybridized. Now, if it was sp3, remember, we wouldn't have a p orbital that can overlap with another carbon's p orbital. We would have an sp3 hybridized orbital that would probably be at a slightly different angle. And so we wouldn't have the ability to move these electrons around, or the electrons wouldn't naturally delocalize. Okay. So in summary, by adopting sp2 hybridization, carbon 3 can share its electrons with other carbons, which is more stable. So atoms want to be as stable as possible. So again, in this instance, that carbon is going to adopt an sp2 hybridization in order to share its electrons with the other carbons. All right, so I think I'm going to stop there for this lecture. You've already seen me accidentally hit the next button here. But next time we're going to talk about the basic rules of resonance, and we'll go over some more examples of resonance structures. So I will see you then.